All right, so. Okay. Okay, hi, I'm Charles Steinkuhler, and going to have a very, very brief introduction to some low-level real-time synchronization issues and memory access problems. We've seen in presentations so far several interesting modular systems where one system's talking to another, one piece of HAL is talking to another piece of HAL. We have real-time talking to user mode. All that has to happen through synchronization mechanisms. And we'll talk a little bit about that as an introduction to Michael's talk coming up next about all the new HAL features. So very briefly what we're going to go over here. Back in the old days, microprocessors, when I was getting into computers, you had a few megahertz clocks. Memory accesses took many clocks. When the computer did a read or a write to memory, it just happened, and the computer just waited around until it was done. And you didn't have to worry about it. So as computers got faster and faster, they started adding things like caches to speed up the access to memory. And all of a sudden, the real physical memory, what was visible outside the microprocessor, no longer matched the microprocessor's logical view of what memory was. You had write-back caches, write-through caches, other things. Then this all gets dramatically more complicated when we add multiple bus masters. Those can be things like DMA. All of your hard drives and network cards and various other hardware peripherals are now doing DMA for high-speed access, your USB controllers, as well as there are multiple cores, multiple CPUs, all with independent caches. Each of those is its own independent bus master trying to talk to memory. And so exactly what the contents of memory are is relatively confusing at times. So if you're talking between processes on different cores or different physical chunks of hardware or different HAL instances or whatever, they have to be synchronized. And one of the simplest and basic building blocks for synchronization is atomic access. That basically means atomic, indivisible. You're guaranteed to get the entire value or write the entire value whenever you access it. And there are various ways to generate atomic accesses. You used to have to actually fall down to assembly language instructions and actually execute specific architecture-specific instructions to be able to do an atomic read or write of a specific value. Recent versions of C have added those as standards in C11 and later. GCC and other compilers had various mechanisms for you to be able to do this prior to the C standardization. And for a long time, there have been libraries that would let you do various atomic and low-level synchronization primitives. These are basically what you build everything else out of. If you can't do atomic accesses, you can't really do any of these fancy synchronization mechanisms. And most CPUs of interest today that run Linux anyway have mechanisms to do up to 64-bit data types. So you can share something as complicated as like a double float in a single atomic instruction. If you need to do more than that, you've got to do something a little bit more sophisticated. So some of those sophisticated options are things like spin locks, other locks, semaphores, critical sections. Some of these can be what's termed as lockless. You don't have to sit around and wait and pull a memory location. Others are. Spin lock is sort of the definition of a lock. There's a very classic request acknowledge cycle, which is very robust, also tends to be slow. You have a 4-step dance. It takes a minimum of 4 process thread invocations to go through the entire loop. One side requests something, the other side sees it's requested something, does whatever's requested. Since it sets the acknowledge, the requesting side sees the acknowledge, clears its request. The other side sees the request was cleared, clears acknowledge, and then you can start over again. That works very well. I use that a lot personally, but I do it in hardware where each side can take like a single clock cycle. When you're doing it in thread process invocations, it's dramatically slower. So one of the very common things that's done in for low-level communications and interprocess where you've got asynchronous, you're crossing asynchronous boundaries, is a ring buffer or queue or FIFO, which is what we're going to talk about. And there are a very large number of other options as well. We're not going to even come close to talking about everything. So ring buffer basics, we'll go through this pretty quickly. You can pick up any standard basic computer text and it will go through the details of a ring buffer. This is a very simple version. There's one writer and one reader. So one process is generating data and putting it into the buffer. Another process is looking for the buffer and pulling data out. And zero locks, no locks are needed. Neither side has to block out the other side. They can both be running simultaneously, as opposed to a spin lock or a critical section where you have to negotiate for a particular token or flag to be able to modify a shared data structure. Neither side has to really negotiate or worry about the other side, which is why it's lockless, which is why it's fast, which is why it scales well. So to write, first thing you do is you check and you make sure there is space. You look at the read and the write pointers and see if your buffer is full. If it's not full, you write your data into the buffer, you update the write pointer, you're done. Read side, basically the same process. You look, see if there's any data by comparing the pointers. If there's data, you read it out, you update the read pointer, you're done. This works because it's safe if the read or the write pointers are old. So if you're writing and the read process has been going on while you're looking at the pointers and trying to figure out if there's any space in the buffer, and you see an old version of the read pointer, then you see the buffer as more full than it is, and you don't write anything. And on the read side, the same thing happens. If the write process has actually put some data in there, and you see an old version of the write pointer that shows it a little farther back, you see less data in the buffer than possible. You don't read, and you just wait until the next cycle. So that's one of the ways these mechanisms work without having to have a token or pass a token or a synchronization lock from one process to the other. They're safe with old pointers. That's assuming that your pointers are atomic, so that you're actually looking at, whenever you look at a read or a write pointer, you're looking at the entirety of the pointer and not part of it. If you have a 128-bit pointer and you can do 64-bit atomic operations, you might get a messed up pointer and everything falls flat. But basically, this is a very standard mechanism in computer processing. Been around a very long time. Very safe, very analyzed. There's support for this in just about every OS or real-time type of environment. So what could possibly go wrong? Well, actually, quite a few things if you come down to it. The first is actual logical problems. So despite how simple this appears, it actually is a little bit more difficult to put into practice without making mistakes, especially if you get into things like buffers that are not power of 2 size. If you're trying to use the entirety of the buffer, if the pointers are equal, you can't tell if the buffer is completely full or completely empty. So that brings into the you need a full empty bit, and processing that is complicated. If you're writing various sizes of data into the buffer instead of simply my buffer is n units long and each unit is 37 bytes or something like that. There's lots of ways to mess this up. It is my suggestion that if you do want to use processes like this, you use a library. A lot of people have worked on these. There's implementations typically available in almost any framework you would care to use. You should use those rather than try to reinvent it yourself and create various subtle bugs that you don't find out about for a long time. So those are all logical problems. But let's say you got the logic right, you're using a good library. There's still a number of things that can go wrong. And generally they basically are all various forms of memory accesses being changed or reordered. And how does that happen? Well, one of the first things that will play with your memory access ordering is the compiler itself. So the compiler sees all the reads and the writes that you're doing. And there are specific rules the compiler will obey for determinism so that your program is still doing what you told the compiler you wanted it to do. But there is a relationship between the address read pointers and the data that you're reading or writing. The compiler basically doesn't really know about. So the compiler at high optimization settings is free to pull and move around reads and writes and can actually potentially create code that does the wrong thing that then gets compiled and does the wrong thing when it runs. There's also hardware issues. Speculative reads, that can be done by hardware. That's also one of the ways that a compiler can mess up. Compilers can look at the instruction sequencing and determine, oh, look, you're going to read a value over here, and here you're writing a value, and the way that the clocks work out, if I move this read ahead of the writes, then it'll run faster. So it's trying to help you, but in fact, it actually changes the function of your program. Hardware will do that as well. The read promotions or posted writes, typically in a cache or in any sort of sluggish memory system, reads are given ultimate priority because almost always whoever wants the data is sitting around waiting for it and not doing anything while the read is outstanding. So writes get posted. When you write a value, it gets written to the cache, it gets flagged as dirty, it gets written to the next layer, next layer, next layer cache. Eventually, at some point, it's going to get written into memory. But a read cuts through all of that instantly, pulls directly from memory, because while the read is happening, the CPU isn't running at 3 gigahertz doing a bunch of interesting stuff. It's sitting there twiddling its thumbs, waiting for some data to show up. That's no longer entirely true with the modern processors. They're doing about 18 other things at that same time, all speculative, but we're not going to cover all that in detail. Then in addition, there's also various hardware optimizations that can affect this. DRAM memory now is made up of pages and banks, and you have to access these pages and activate the banks, and specific regions of a DRAM you may be able to access in a couple of clocks. You might be able to access another region of DRAM in 10 or 20 clocks. Then the hardware is going to sort through generally and try to optimize so that it will group the reads and writes and accesses to a similar page together so that it doesn't have to refresh and open new pages. It's very much like an elevator algorithm on a hard drive. It's the same sort of thing. You have regions where you can access faster than others, even though it's like it's memory. It's like the same speed. No, it's not, because inside each one of those little RAM chips are actually 8 banks of RAM chips, and one of them is active, and the others might be. It gets complicated. And on top of that, you don't just have one bank of DRAM chips. Modern processors have 2 or 3 rows of memory, and you've all seen it. It's like, for the best performance on your motherboard, put these 2 modules in, and then these 2 modules, because of the way that the memory is organized. So some of those are actually divided up so that you might be able to talk to one bank of memory faster than the other, and it could affect the memory ordering. That's sort of the path congestion as well. Maybe one of the memory banks is being hit pretty hard, and it takes a long time for your write or your read to get processed there, but the other one wasn't really doing anything, so it happened pretty much instantly. All that can change the order of your memory accesses. So to fix this, there are barriers and fences. You use these to guarantee the ordering that you expect and that you need for your program to run properly. These all vary by system and architecture in terms of what you have available, which sorts of barriers and instructions you have available, and how expensive they are. On the x86 system, a lot of barrier instructions are essentially free because the x86 system is strongly ordered. There's very specific rules about how at the hardware level, bus and memory accesses can be shuffled around. The ARM system is far looser, and something like the DEC Alpha system, if anybody remembers those, is dramatically looser still. So depending on the specific system architecture you're running on, some of the barrier instructions might be very expensive, or they might be essentially free. And they range from, like I said, essentially like a no-op all the way up to invalidating the cache. Obviously, if you turned the caches off, you'd sort of be back to where you were with the microcontroller, but your 3 gigahertz processor wouldn't really run very effectively if you disabled the L1, L2, and L3 caches that are sitting there in the, on the die. So there's also compiler barriers. Those don't actually make it down to the hardware at all. They are simply instructions to the compiler that there's a line in the sand, and the compiler is not to move any speculative reads or writes across that line. And the hardware ones are very much the same thing, except they go all the way down to the hardware. And there are, depending on the system you're running on, different types of those as well. One will simply guarantee the ordering of the memory accesses and let the processor sort of continue on its merry way. And another actually says, wait here until the memory has actually been written. So again, going back to the hard drive analogy, if you're thinking about something like a database or some code that's reading or writing disk, you can do a write and just sort of continue on. Or you can do a write and say, I want to make sure that before you come back to me, this data is really actually on the drive. So basically, there are similar hardware fence instructions for that, and they're used, and it's for exactly the same reasons you have the different versions in the software world. And then also to make it a little bit more complicated, you can generally specify the desired direction, whether you're concerned about reads or writes, and in some instances the domain. So domain would be like there's a single core, or maybe there's 4 cores on your CPU. Is the domain like the L1, the L2 cache, the L4 cache, physical memory? How far out are you concerned about that data actually being propagated before execution can continue? And those are some of the things where if you use the wrong one, it works 99.999% of the time, but in the one corner case that you forgot about, it just falls flat and you get strange weird bugs. So going back to our ring buffer, we do pretty much the same thing. To write, we check and make sure that we've got space. We actually write our data, but then what you have to do is you have to execute a memory fence instruction. And it has to be the proper instruction that ensures that all of the data that you wrote is written out to memory somehow and is seen by any other observer in the system that's concerned about it prior to the next step, which is updating the write pointer itself. Otherwise, if somebody sees that updated write pointer before the actual data got flushed out, obviously you could have bad things happen. A possible enhancement here is also you may want to follow the update the write pointer with something that actually pushes the write out to the system, so it doesn't just sit around in a cache. But that depends on the particular system you're on, and it's not absolutely necessary. It can help or hurt the performance, kind of depending on what system you're on. And reads, again, basically the same thing. You want to check for whether or not there's any data available in your buffer. If there is, go ahead and read the data. Then it doesn't seem like you would, but you actually do need a memory fence that says, make sure that all of the data read up to this point, all the data reads up to this point have actually completed before you read the next one. Because again, reads are given very high priority, but if you're reading a big chunk from a buffer, probably that's in contiguous memory, probably that's coming from one specific chunk of DRAM. The read pointer could be someplace entirely else. It could take a microsecond to read the data that you've got from the bulk data from the buffer, versus maybe 100 nanoseconds to read the data for the read pointer. So if you go off and read the updated read pointer, haven't finished reading the data from the buffer, systems are actually fast enough now. The write process could write over the data that you were still trying to read before you actually read it. This does happen. You can actually set up synthetic tests and watch this sort of thing fail. So that is, in brief, some of the synchronization stuff. This is a lot of this relates to what Michael has been doing with HAL, which is why I'm going first here. But there's another aspect to this besides simply getting the ordering correct, and that's cache effects. Obviously, each CPU typically has its own cache. These days, especially on x86, 2 or 3 or 4 caches. There's L1, L2, L3, L4. You got a lot of caches everywhere in the system. So how does this work? Okay, you've got if you're communicating data across processes, sort of by definition, you're trying to share the same memory space between a couple of different processes, or typically that was going to fall onto a couple of different CPUs in today's world. So at a hardware level, the caches have a variety of complicated state information they track for the status of each of their cache lines. If it's empty, if it's full, is it is it fresh, is it empty, is it invalidated, is it, what is it? So this propagates through the system, but it propagates at a generally slower rate than the data itself. So one of the things that you don't really want to do is mess up the cache control logic and basically start thrashing your cache communications channels. So lots of having the same data present in lots of different caches is not really a problem. They all say, hey, I've got a picture of this data. It's current. I'm reading it. I haven't done anything to it. When you start writing to it, then you have an issue of, okay, I've changed this data. The cache has to essentially take ownership of that cache line. Typically, it's an entire cache line. It's not a single byte. It's not a single D word. It's a cache line. 64 or 128 bytes typically, depends on your architecture. So if you've got your read and your write pointers, say, right next to each other, the read process is updating the read pointer, and the write process is updating the write pointer. Well, that's fine. It all works logically well. And I said this is a lockless synchronization mechanism because those don't have to interact. But if you have both of those present in the same cache line, it becomes a locked operation at the hardware level, because the hardware caches have to basically negotiate for who's got the right version of the current memory space. So they basically start fighting over which one is the correct version, and that process is extraordinarily slow when compared to the general memory access process if you were just running along reading and writing normally and not fighting over memory space with another processor core. So essentially what that boils down to is if you're running on a single core and all of your real-time code is locked to a single core, which is the way Linux CNC has historically done it. And typically one of the things they advise doing is assigning a processor core to real-time, and that's the real-time core, and that's it. You want to pack all your data as much as you can into the cache line, because you fit as much data as you can into the cache. And obviously data in the cache you can access faster than anything out in memory. If, however, you have multiple cores, that can cause horrific performance problems as the cores fight over who owns the cache lines. And you're much better off spreading the data structures out so that what one process is rapidly accessing is not in the same cache line as anything else another process is trying to rapidly access. So that is a very, 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 very quick and high-level overview over some of the problems that are encountered at a low level. These are the kinds of things that people typically don't have to worry about when you program. Most people don't think about these things. You just write your code, and this is several layers removed from anything you might be concerned about. But when you're talking about high performance, you're talking about real time, you're talking about multi-processing, multi-threaded systems, it becomes important. And I go back to what I said about the ring buffers, which was use a library. This is hard stuff to do right, and even the people who do it kind of for a living have difficulties getting all the corner cases and everything working correctly, especially across architectures, the way that Linux runs on many different platforms. So that is sort of the introduction to Michael's real-time HAL and some of the changes that he has been making. I have some references here if you actually care to read more about memory barriers. The memory barriers.txt, which is part of the Linux kernel documentation, has an excellent overview of the mechanisms available within Linux for handling memory barriers. That's not, it covers a little bit some of the different architectures, and it's not as, it, for instance, doesn't cover near the complexity that is available on the ARM architecture, but it's a great general introduction. For the ARM specifically, the next link, From Weak to Weedy, is a great presentation on some of the various complexities you can see in a weak memory order system like the ARMs. Then there's a couple other links down there, generally about the Linux kernel development. Second edition had a good chapter section on memory barriers, and Linus commented on the compiler barriers. I was mentioning the compiler will move your data around a little bit. There's a barrier macro, the barrier bracket, available in Linux, and Linus talks a little in that email about why that's there and how to use it, and the fact that it does basically turn into a no-op on most systems. It's a very inexpensive instruction generally, because you're not actually forcing any cache invalidation or any specific physical thing to happen. You're just telling the compiler, don't optimize across this line because you don't know what you're doing. I know more about the code than you do. So your choice is essentially either get rid of optimizing compilers so that they don't do these fancy tricks, or occasionally tell the optimizing compiler, stay away from here because you don't know how to do it right. So, and that's basically what the barrier macro is for. So anyway, those are available online. The presentation is also available online, and should you care to, you may use this under the Linux documentation license. So yeah, we'll leave it on the references. Oh, any questions? Oh, questions, yes, questions. I'm sure you're all enthralled. Which specific cache memory instruction should I use in this case? No.
I know Linux CNC when we came multi-cores, especially around the dual core period, they were having a real hard time getting RTIOA or RTAPI running efficiently on one core. There was some kind of there was a restriction to sharing.
Yes. Yes. And that's exactly the problem. And Linux CNC, as I said, packs HAL intentionally, because HAL is created with shared memory, and they intentionally pack the data structures so that more of it fits into the cache, as much of it fits into the cache as possible, which is great, until you get to the point where I'm running on multiple cores, and then the caches are all fighting over who gets to own the cache line. Yeah, it's and it can cause. I mean, it can cause like 3, 4, 5 orders of magnitude worse performance. It's dramatic. It's not a trivial like, oh, it runs a little bit slower. It can run thousands or hundreds of thousands of times slower if you don't properly deal with that. And that's also one of the reasons why they basically haven't changed that. It just you're recommended highly to lock the real time onto a single CPU, and that's a big part of why.
It would be not handy if you could actually specify a cache specifically for a core. So you can actually take the multiple caches that are there on the die. Now, that's it.
The newer Intel CPUs have a feature like that, and I think it is in the pipe for Linux to be able to partition caches.
Microphone.
Oh, okay. Sorry. The more recent Intel CPUs have a feature where you can actually partition caches and assign them to specific tasks, so there's no contention between those tasks.
And,
But that
yeah,
is
you
not implemented in the kernel yet. It is in progress, I heard.
The real-time Linux version.
and locking specific portions of memory into the cache so that you know, and you can say exactly, you know, like, this is the really high performance stuff I'm worried about, and the rest of the stuff can fight over the rest of the cache that's left, but I want this chunk of it dedicated to my application. There's some of that that's available, but a lot of times trying to tune some of that stuff is, unless you need the very last little nth bit of performance, you're just wasting time, because it works today for this architecture, and then tomorrow the caches are different and the processors are different and they're 3 times as fast, and it's, you know, you have to choose the battles you fight for performance optimization. That's a little bit of the, you know, Michael and I had some discussions back and forth on that with some of the things he was doing for HAL. He's like, well, do you optimize memory? Do you optimize cache alignment? Do you, you know, and, you know, it's a different world today than it was when HAL was first written. And, you know, memories and caches are phenomenally huge now. All of HAL's shared memory would pretty much fit in most of the level 1 caches. Whereas, you know, back in the day that it made sense to pack, now it doesn't. So it's just some of those things. So, other questions? Okay, thank you all.